Okay, and so today we're going to look at the intermediate value theorem, which is often abbreviated as IVT. And the intermediate value theorem is one of the important theorems that comes up in calculus. It's a pretty basic idea. It's almost a little bit intuitive, but you need to see it and you need to know how to work some questions with it. So what the intermediate value theorem says, that if you have a continuous function between two values, so a value like a and b, so a value between a and b, the function would take any value between f of a and f of b over the interval. So remember, f of a would just be like the y value for a at the x value of a, and f of b would be the y value at the x value of b. So notice all these points, kind of zoom in, point A, f of a, b, f of b. So there's a few different things that could happen, I guess. I mean, you could go from this point directly to this point, the most direct way that you could. And what it's saying is, as long as I draw a continuous line here, which I did, then it's going to take on all of these y values. It can't skip any y values. So to help you see that a little bit, let's say that this was in fact like 1, this was 4, and let's say this point was 1, 1, and this point is 4, 4. So all it's saying is, if it's continuous from this point to this point, then it's got to hit all the y values. So it's got to hit every y value between 1 and 4. So somewhere in there it hits 2, somewhere in there it hits 3, somewhere in there it hits 2.1. It guarantees that you hit all of those y values in between. Okay, so in this example, it looks like it hits each y value once, but it doesn't have to be like that. There could be some back and forth that's still continuous. So it may take on this y value multiple times, but it would, what the intermediate value theorem is saying is that it has to take on all the y values from here to here at least once. Okay, so that's all it's trying to say. So if you would try to pause this video, and over here what I'd like you to do is to connect these, make them continuous, and then resume the video. Okay, so no matter what kind of, any way that you connected these dots and you made it continuous, whether you made it a little more crazy or pretty much to the point, what I can guarantee you is that it hit every y value from here to here. So that's continuous. So I don't know, give yourself some points here. I think that maybe helps you see. Maybe that's the point 22, and maybe this is the point 4.7. If that's really the case, then it hits all of what the intermediate value theorem is saying, is it's going to hit all the y values between 2 and 7 at least one time. And that is guaranteed as long as it's a continuous function. So no asymptotes, no holes, no jumping around, none of that kind of stuff. If it's continuous, we're guaranteed that it hits those y values. Alright, so if you read this in a textbook, it would say, the more formal definition, that any value L between f of a and f of b, so that would be like, I don't know, maybe here was my L. L just needs to be between f of a and f of b. With a value c in a to b, so this one hits here, so they're calling this where it hits C. This one hits here, 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 and here, potentially. So at least one of those would be at C. And this one hits in infinitely many spots, it looks like. So one of those could be at C. So that's what they're saying, where f of c equals L. At this x value, it has a y value of L. At this x value of c, it has a y value of L. And at this x value of c, it has a y value of L. So same thing that I said, just a little more formal definition. Okay. All right, so let's use IVT to show that the function has at least 1, 0 in this interval. So this is a polynomial, so I know it will be continuous. Okay, and I'm looking at the interval between 1 and 2. So I don't know what this graph looks like, and I don't want to spend the time to figure out what it looks like. But what I could easily do is I could figure out what f of 1 is. So the y value in x is 1. And by plugging that in, you would get 1/16 minus 1 plus 3, which comes out to be, I'm going to speed up just a little bit here by cheating with my calculator. Of course, I could get a common denominator and all that kind of stuff. 33/16. Okay, so that's a little more than 2. So up here somewhere. Okay, and then by f of 2, I could plug in 2 into the function. And I'd get 1/16 times 16, which would be 1 times 2 to the 4th, which would be 2, 4, 8, 16. And, never mind, that was part of that. So minus 8, and then plus 3. So this would be -5 plus 1, which would be -4. So somewhere down here. Okay, so the really significant thing about these two values is that this one is positive and this one is negative. So this one was above the x-axis and this is below the x-axis. And because this is a continuous function, even though I don't know what this looks like, intermediate value theorem guarantees that I'm going to hit all of those y values between 33/16 and -4 at least once. So that is guaranteeing that there's at least 1 0, at least one time where it has a y value of 0. So if I had to formally give a justification, I would say that because this is a continuous function, f of x is a continuous function, and f of 1 is 33/16 and f of 2 is -4, the intermediate value theorem guarantees that we would hit each of the y values in between, and so 0 certainly is in between 33/16 and -4. Alright, question 2, verify that it applies and then find the value of c. Okay, so the verifying that it applies is kind of like what we just did a second ago, except maybe not for 0, maybe it's 11, or maybe it is 0. But again, I really could figure out what this graph looks like, and it's just a parabola, so it wouldn't really be that big of a deal to figure out what it looks like. But that's not really the point here. I could figure out the y value at the left bound, and I could find the y value on the right bound. So 25, 30, 29. So if you need a visual here, when x is 0, it is at -1. And then by the time it makes it to x is 5, it's all the way up here at 29. So because this is a polynomial, I know it's going to be continuous. And so I don't know how much back and forth it has, but I know if it's continuous, it can't be jumping around or be missing any values. It's got to hit all of the values like 11 at some point. So that verifies that it works. 11 is certainly in between -1 and 29. Now the second half of the question, find the value of c that's guaranteed by the theorem. So take f of c, it's like f of x. So everywhere there is an x, plug in a c, and figure out where it equals 11. Okay, so then you've got a quadratic to solve. So quadratics, we like to be in standard form, put it all on one side equal to 0. Looks like this would solve with factoring and -4 and 3. All right, so I know this function has a y value of 11 at -4 and 3. The one that was guaranteed by the theorem, though, would be, well, I was really looking at values between 0 and 5, so the one between 0 and 5 is 3. So -4 also worked, but it wasn't guaranteed by the theorem, at least not the bounds that I had checked. Okay, so number 3, if you go ahead and pause and see if you can do the same thing I did for you in number 2, and then unpause the video, please. Okay, so left bound has a y value of 8, and the right bound, let's see, 9 plus 8 would be 17, and minus 6 times 3, so -1. Okay, so visually, you don't always have to make a visual, but I'm doing it here to help you see. For this x value, you have a y value of 8, and for this x value, you have a y value of -1. And again, polynomial, always continuous, no holes, no jump discontinuities, no infinite discontinuities. So I don't know what it looks like, but IVT guarantees that I hit all these y values at least once. Specifically, y equals 0. So f of x, f of c just means you plug in a c everywhere there is a x. And this time I want to figure out, when does it equal 0? When does the function have a y value of 0? All right, well, solving a quadratic again. So I guess sometimes you'd have to pull out quadratic formula, but I try to get away with factoring. Looks like it has a y value of 0 at 2 and 4. And the one that you should have selected would be 2, because we were really only interested in between 0 and 3 for this question. So I guess 4 technically has that same y value, but my work was not guaranteeing that this one would exist. My work here with intermediate value theorem was guaranteeing that one existed, and it was that one.